There is no engine on this roof, no fuel tank, and no rotating generator. Yet sunlight is producing useful electrical power for the entire home. The complete system performs several connected tasks. The modules create direct current, the inverter converts it, and the energy is used, stored, or exported. A solar module is a sealed, layered machine. Glass protects it. Encapsulating polymers secure the cells, and copper connections carry the electrical output. Sunlight arrives as packets of energy called photons. The surface coating reduces reflection, allowing more of that energy to enter the silicon. The active component is a thin silicon semiconductor, engineered with different electrical regions and metal contacts that collect the generated current. Sunlight arrives as packets of energy called photons. The surface coating reduces reflection, allowing more of that energy to enter the silicon. When a photon transfers sufficient energy, it creates a mobile electron and a corresponding positive vacancy inside the semiconductor. The junction's built-in electric field separates the newly created charges before they recombine, establishing electrical voltage across the cell. Fine metal fingers collect the charges and guide them into larger conductors. When the circuit is complete, direct current begins to flow. A single cell produces limited voltage and current. Many cells are interconnected so the complete module can deliver useful electrical power. The cells are sealed between glass and protective polymers. They provide insulation, mechanical support, and resistance to moisture. The junction box connects the cell strings to the external cables. Bypass diodes provide alternate paths when part of the module is heavily shaded. Modules are connected into higher voltage strings. Their direct current travels through secured cables, disconnects, and protective devices toward the inverter. Solar output changes with sunlight and temperature. Maximum power point tracking adjusts the electrical operating point to extract the greatest available power. DC-link capacitors temporarily store small amounts of energy. They distinguish themselves from batteries by acting fast, voltage. This occurs just before the final conversion stage. Power semiconductors switch the direct current extremely quickly. Inductors and capacitors then shape those pulses into alternating current. Before connecting, the inverter measures the grid and matches its voltage, frequency, and phase. Only then can power flow safely connect. The home uses available solar energy first. Its breaker panel distributes that power to the circuits and appliances currently operating. When solar production exceeds household demand, the unused energy can pass through a bidirectional meter and enter the electrical grid. A hybrid system can store excess solar energy. The battery management system monitors cell voltage, current, and temperature throughout charging. At night, the panels stop producing useful electricity. Stored battery energy can supply the home until its designed reserve level is reached. When one substring is heavily shaded, its current falls. A bypass diode provides an alternate path, reducing but not eliminating the power loss. Strong sunlight supports production, but higher cell temperature generally reduces voltage. As the panel becomes hotter, electrical power can fall. Panel tilt and orientation affect how directly sunlight reaches the surface. The best arrangement depends on location, roof geometry, and energy goals. Disconnects, breakers, surge protection, grounding, and anti-islanding controls protect the equipment, the building, and the electrical grid. Sunlight creates mobile charges. The modules generate direct current, and the inverter makes that power usable. The home can use, store, or